Welcome back to part 1 of our series on pacemaker battery technology. In this lecture 3, we're diving into the chemistry behind the pacemaker battery technology. Here are two examples of early battery technology. One is a nickel-cadmium battery, and the other one is plutonium batteries. Another example of early battery technology is the mercury oxide zinc battery, which has a very flat discharge curve, and the delivered 1.3 volt cell voltage. A small amount of hydrogen gas is created in reaction by the product, so it needs venting in the generator shell, and this is more prone to fluid infiltration. This table shows the difference in the cell voltage of current battery technology. Cell voltage determines the battery's ability to generate pulse energy and charge the defibrillator. The battery with lithium iodine has 2.8 volts of cell voltage. A battery with lithium manganese dioxide has 3.3 volts of cell voltage. The battery with lithium carbon monofluoride has 3.1 volts of cell voltage. A battery with lithium silver vanadium oxide, commonly found in ICDs, has 3.2 volts of cell voltage. Let's deep dive into the basic functions and electrochemistry of batteries. A battery converts chemical energy into electrical energy. The source of this energy is electrochemical reactions that occur within the battery. The type and amount of material participating in this reaction determine the deliverable energy of a battery. It's time to focus on battery technology. The major parts of a battery are the anode, the cathode, and the electrolyte. The anode and cathode must be physically separated, and both must be in contact with the electrolyte. The two battery components involved in the electrochemical reaction during discharge are the anode and the cathode. The anode, usually lithium in most medical batteries, furnishes electrons for the external circuit, whereas the cathode, usually an oxide or halogen-rich compound, receives the electrons. The anode is defined as the electrode at which electrochemical oxidation occurs, and the cathode as the electrode at which electrochemical reduction occurs. This schematic diagram is the representation of a sealed battery. The anode material is on the left, the cathode material is on the right, and the electrolyte is in the middle of the cell. The discharge reaction is A plus C equals to AC. In this example, both A plus and C minus are mobile ions, and the discharge product AC is insoluble and precipitates in the electrolyte solutions. The lithium silver vanadium oxide battery is used in the majority of ICDs today. It is optimized for pulses of high current to charge the defibrillation capacitor, quickly known as high-rate batteries. The desirable characteristics of battery technology include high energy density, low self-discharge, small size, a highly predictable discharge curve, and solid-state chemistry. The image on the right shows an early pacing circuit designed by Elmquist. Longevity is typically defined as the interval between device implantation and the detection of an end-of-service indicator. Because therapy can vary substantially from patient to patient, the longevity requirement is typically linked to a specified set of nominal conditions and programmed parameters. The minimum battery capacity required to achieve the specified longevity can be calculated from the average current needed for this nominal set of conditions. The battery capacity is measured in the unit of amp-hours. If a battery has 1 amp-hour capacity, and the circuit drains 0.5 amps per hour, the battery would last 2 hours. If the circuit drained 1 amp per hour, the battery would last 1 hour. The battery used in pacemakers ranges from 0.4 to 1.5 amp-hours. The current drain is measured in microamps. The relationship between battery capacity and current dryness is that 1 amp is equal to 1000 milliamps, whereas 1 milliamp is equal to 1000 microamps. 1 amp-hour battery has 1 million microamps of available capacity. When the pacemaker output stimulus is not delivered, the pacemaker drains an average of less than 10 microamps of current per hour. These 10 microamps are used to run the circuit, while the pacemaker is inhibited. Next, we move on to the factors that affect current drains, which includes pulse amplitude, pulse width, pacing rate, pacing mode, percentage of pacing, and lead resistance. When the pulse amplitude and pulse width are increased, the current drain is also increased. When a pacing mode is changed from one to another, the current drain also changes. When the pacing percentage is increased, the battery longevity is also reduced. Excellent. That concludes our exploration of pacemaker battery technology in part 1 of this course. We've covered the fundamental principles that govern their functionality. In the next lecture, we'll shift our focus to the properties of pacing leads, the vital components that establish the connection between the pacemaker and the heart. Leave a comment below with your guesses. And be sure to subscribe and hit the notification bell so you don't miss the next lecture. See you then.